Okay, let's come back to the concept of utility. So we have defined utility of the state sequence to be the individual sum of the rewards which you will be getting at every state. But there would be a problem that the sequence of state, what if the sequence is infinite? What about reward? If the basic value of the reward is a negative value, so this goes something towards minus infinity. So that's not correct. So we should have some way out to resolve this particular problem. So here, the idea would be that we can give a discount factor so that the nearer states initially to which are closer to S naught, which is the initial state, they should be given the reward as they were there. As I'm moving away from the initial state, then the reward should be discounted by a factor. Like in this case, we are considering the factor to be gamma, whose value is between 0 and 1. If you see over here, so at every step, as I'm moving away from the initial state, the factor gamma tries to make the sum in such a way that it should not go towards minus infinity in case the initial rewards they were a smaller negative value like minus 0.04. Okay. So with this, if you try to solve, so it is bounding a result that it is not going towards minus infinity in case we are having infinite sequence. What we are saying is sooner reward should be given more weightage than the later rewards, so that this utility is bounded, and I can deploy some algorithm. Obviously, we want a suitable path which can maximize this utility. So the algorithm needs to converge. Now, so utility of a state when you are given a policy, and if the state sequence is starting from S, so the expected utility looking at the policy over the state S is given by a summation of whatever be the state sequences, but it is starting from S, is probability of the sequence into utility of the sequence. So obviously we want this utility to be maximized. Okay. So how do we find the utility of a given state? So let's say initially we are on state S. Over S, there are certain actions which are applicable, and we'll be picking a suitable action to move to another state S dash. So what is the expected utility of taking an action A in state S? I'm taking an action A, so this was the expected utility as you have seen in the previous formula. How do I choose the optimal action? I want to vary the actions over there. I would like to pick that action which can maximize the reward value. Okay, and that will be part of my policy. That action I'll pick will be part of my policy. So recursively, I can define this utility in terms of the utility of the successor states. Now, let's see this out. So what we are saying is utility of a state sequence is defined as the individual sum of rewards, and now we are calling it as discounted rewards, so that the problem of infinite state sequence is resolved. Now, the policy is the maximum expected utility, as you've seen in the previous slide. So therefore, the utility of a state is the immediate reward for the state and expected utility of next state. Let's see this out. So there's a Bellman equation which caters a relationship between utility of a given state with the utility of the successor states. You see over here. So here it says that utility of a state is given as reward of the state plus gamma time, whatever be the best action that you might have picked, depending upon this overall expected utility corresponding to the successor state. So this is the Bellman equation, which was invented by Richard Bellman in 1957. Let's see this out over this example. So we want to find out the utility of state 1, 1. So this is the state whose utility I'm interested in. I do not know what is the best action. I can move up, I can move down, I can go left, I can go right. I don't know what is the best action. So I need to try for every action and then see the result. Let's see this out. We'll see the up action. Okay. Let's say moving up. Just a sec. We want to move up. Okay. Assuming up to be the desired action. So far we do not know whether this is desired or not. Let's assume that way, that moving up is the desired action. So what we said, as per the concept of Bellman equation, utility of a given state is equivalent to utility of the reward of the state, which is minus 0.04 plus gamma times max of. Now, if I'm picking up as the desired action, so what are the different actions possible? Either I can go left, okay, or I can go right, or I can go up, or I can go down. I can pick any one of them. So let's analyze them. So if I'm going down straight away, I'm moving opposite to the desired. So for this probability is 0. That's why we have not included it in the stop code. Now let's pick this left one. If I try to move left, I will bump with this one and move back to the same state. State is clear that I will land in the same state. So the state is 1, 1. So whatever be the utility of the state, we'll pick that time. Now what is the probability? Again, the same rule. The desired action, in this case, you have selected it to be up. You're standing at this point, looking in this direction, stretch your arms and see where is this point. Is it towards the left side or towards the right side? We'll come to know it is towards the left side. So when we are moving in the left of the desired, then the probability is 0.1. So that's why 0.1 I will apply. Okay. If I try to move right, means this direction now. Again, you're standing at this point, looking at the side, stretch your arms and see where is this direction. So this is the right side. So right probability is 0.1. If I take this action, I'll reach to this room, which is y. This room is 2, 1. So whatever be the utility of this room, you will add. Third action is I'm moving in the action of the desired action. So 0.8 is the probability. You land up in this room. This room is 1. Okay. And accordingly, you will compute it for left as the desired, down as the desired, right as the desired. And accordingly, one of the 4 values is the maximum. We will pick that as a value, and that action will be stored in the policy for this particular information. Okay. Assuming that this is the best action at this point of time for a particular state. Now, so if we talk about the Markov decision process, we are having n states in total. So every state will be applying the Bellman equation. There are n Bellman equations in total. So n equations, n unknowns. So we need to solve. So here, if you see in the Bellman equation, there was a max function. Max is a nonlinear function. So I cannot apply linear programming over here to solve it. Rather, we need some kind of an iterative technique to solve the problem. So there are 2 methods, value iteration, policy iteration. We'll see them one at a time. In value iteration, the objective is to build a policy. How is it possible? We will first compute the utility at every state, and then based upon the utility, you will select the suitable action as per the Bellman equation, if you remember. Okay? And then iteratively try to tune in the values of the utility corresponding to every state in different iterations. So when to stop? When the utility is not changing, or when the directions that you have taken, they are not changing. Or if you want, you can iterate it to maybe 100 times. So after the 100 iteration, then you will stop. So it depends how you want to update the things. The same is written over here in the form of the algorithm. So initially we'll start with zero utility. We'll keep on iterating until the convergence condition is met. We'll discuss the convergence condition. So during any iteration, let's say the ith iteration, we'll use the Bellman equation to solve it. So this is this code for value iteration method. Now, so what is the effect we have over the utility, and accordingly we need to mark out the policy. In case if my G, in this case it was gamma, if my discounted factor is 1 and the reward for being in every non-final state is minus 0.04, what is going to happen? So after execution of the policy value iteration method, so this is the utility corresponding to all the states at the end after convergence. Okay, and this is the policy at the last iteration. So these are the arrows that you see over here. This is the best action one can take at any state, keeping in mind that this was the reward. Obviously, as we have discussed in this case, since the reward is very small, I don't want to take any chances. I'm okay with by going into a longer path and solving the path. Try to solve this example first by yourself. So here in this case, this G again, which is this gamma, is 0.5. The reward corresponding to every non-final state is minus 0.04. There are two final states, +1 and -1. Utility of every state is 0. This is the state X, which is marked over here. So you tell me the value of utility of this X in 2 iterations. So what is the utility of X in first iteration and then in the second iteration? I hope you remember the Bellman equation. On X, I can take 4 directions, out of which one is the suitable one. One of them is suitable. I think it is very easy for us to see that if I'm at this state X, I should be moving right, and this is the best action I would be taking. Even you can verify it. Initially, value corresponding to every state, utility value is 0. Now you need to see it for X for the first iteration. So see this out. So we have chosen the best direction, which was this one only. Okay. And if you see, this is nothing but the Bellman equation. So this is R value, this is gamma. Then these are your values corresponding to the possible actions. Like if I'm moving in the correct direction, so this was the value. One value could be I'm moving either upwards or either downwards. Because moving towards the left side, which is just the opposite to the desired, is not required because the probability will be zero. So accordingly, these are the 2 values for the 2 other arrows which I will be mentioning. We came to know that 0.36 is the utility after the first iteration. Then for the second iteration, now no longer the utility of every state is 0, they would be having certain values. So for X, I require these 2 states. Okay, now they might have changed from 0 to some other value. Okay, So accordingly, you compute it for the second iteration. Here we came to know that it got increased from 0 to minus 0.04. Okay. Again, what is the utility? We know that for sure if we are at the state where 0.36 is written, so moving right is the correct action. Again, using the same logic that we have seen in the previous slide, try to solve it and see the utility of being in state X is 0.376. The same thing has to be replicated for every state and try to solve until convergence condition is not met. We get to know the final utility values and the policy. Now, what is policy iteration method? In policy iteration method, we have some policy. Initially, we have some policy. If you do not have, you can randomly assume certain actions corresponding to a state. You'll get some policy. Then you can try the policy over this concept of utility that we have seen, the Bellman equation, and see whether it works or not. If it doesn't, try to update certain values. So what is the benefit it is offering? If we have some initial policy with us. In value iteration, we were not looking for the policy. Okay, rather we were simply solving those Bellman equations. Now let's see this out. So here, what is the benefit it is offering? If we have the policy, we know what is the best action at that point of time per state. That means that max factor, which was there, is now no longer part of the Bellman equation. It is gone because we have the policy. If max is gone, now the complete equation that we see is linear in nature. We have L Bellman equations with n unknowns. The equations are linear. I can solve it in order of input time. Okay. So it is reducing the time complexity that. Okay. So what happens is we have a policy. Based upon that policy, we compute the utility, and if required, we'll try to update the policy by checking the other directions, whether they are performing well at this particular iteration or not. We'll start from initial policy, we'll be calling it as I naught, and then perform the following steps. First is policy evaluation. So since we have the policy, so we'll calculate utility of a given state based upon the policy, pi I, means the ith iteration. Then look for policy improvement, whether this pi I plus 1 needs to be taking the same value of pi I, or I should update. How should I update? You know from the Bellman equation, the action which maximizes the expected utility, that action needs to be picked up. Okay. So given a fixed policy pi, we compute the utility of every state S by the Bellman equation. So this is the Bellman equation. Now, since here we have the policy, so we know the action. A, we need not worry about what is A, because A is already there in pi. So, in case our policy is fixed, this action A, which is over here, we know it is part of the policy, which is in pi. Yes. So this max term is gone. See over here. Do not worry about it because we already know the action. Okay. So this can be easily solved since it can form a linear system of equations and equations. And then accordingly you can update the policy in the next iteration. So this is the policy iteration algorithm. Okay. So if there's a change in the policy required, I'll look for the other actions which were unexplored, and if they're performing better, we'll update the policy. So we found out that it is an efficient approach compared to the value iteration method. So it is working in order of input time. Okay. So in today's lecture, we talked about the concept of reinforcement learning. We have introduced how to model the reinforcement learning problem through Markov decision process, with policy as a solution to the process. We have seen the concept of infinite horizon, where if the state sequences are infinite in nature, then how would my utility be calculated? So we introduced the concept of discounted rewards over here. And then for computation of the policy, we have seen two methods, which were value iteration and policy iteration methods. So this is all from my side today. Thank you so much. So please feel free to ask me the questions. So this is my email ID mentioned over here. Thank you once again.